Well, dear students, see, this is a second law of thermodynamics. I have written only the second law because this is thermodynamics chapter. So no need to write every time second law of thermodynamics. See, second law of thermodynamics, this gives the idea about the entropy, how entropy is defined. But before going into the details of this second law, regarding this second law, different scientists have given different approach to define the second law, different definitions they have given. So first, I will take up some of those definitions which are important to you and try to make the ground for explaining this entropy. Although in thermodynamics first law, in the end of the thermodynamics, not thermochemistry, at the end of thermodynamics I have calculated this q by t, q by t, q by t in various processes I have calculated, and that q by t is a constant, and it becomes the state function that I have already shown you. But see, before going into the detail, what first law tells, first I will start from the first law. See, the first law tells about delta E is equal to delta Q plus delta W PV. As we know that this is a basic equation. I'm not writing here PV, just I'm writing W. Okay. So let's start the discussion of second law from this first law, right? See, this equation, if you consider a cyclic process, because in the definition of entropy certain keywords are very important. So one keyword I have started here, that is cyclic. If it is not cyclic, the process is not cyclic, then the concept of entropy you cannot understand, because then the role of energy is also coming there, right? So suppose that we have a cyclic system or cyclic process, right? Cyclic processes, like cyclic process. So for cyclic process, this delta E is equal to 0. Means what? Energy is conserved. In the whole cycle, the energy is conserved. In this situation, what will happen? This first law, this expression, you can write now Q is equal to delta Q is equal to minus of W. This is very important relation. This suggests this. First law suggests that an engine, any engine can run in a cycle, and convert heat to work completely. See here, the keywords are here: cycle, heat, work, and the other important word is here, completely. See, completely. So this conclusion we can draw from the first law. Okay. if an engine which is running in a I mean in a cyclic manner, in that case it is possible for us to completely convert heat into work. This is the suggestions or inference we can make from this thermodynamics first law, right? Clear? Okay. Now, is this, is it possible? Is it possible practically? The answer is no. So this is the rule of second law, that second law puts the restriction over the complete conversion of heat into work, right? So second law, first, I mean first important application of this second law is, or application of this second law is that this puts the restriction restriction restrictions on the complete conversion of heat to work, right? So this second law, the first application of the second law is this, and the second is provides a set of principles for determining the determining the direction of spontaneous change, and determining equilibrium state of system. Equilibrium state of system, right? So this second law basically, this is the application of second law. This puts the restriction on the complete conversion of heat into work in a cyclic process, and provides a set of principles for determining the direction of spontaneous change and determining the equilibrium state of system. So this is the role of this second law in this chemistry, right? And before this, what I mean scientist, or what scientific fraternity thinks about or thinking about this spontaneous changes, that people are thinking that if delta H for any reaction is less than 0, then the process is spontaneous. Spontaneous means the process can proceed in the given direction uh, without help of any external source, right? So the correct word is here, determining the direction of the spontaneous change. See, if any reaction is non-spontaneous in left to right, so it may be possible that right to left it is spontaneous. So direction is very important here. So spontaneous in the given direction. In the given direction means the direction in which delta H is less than 0. Is spontaneous in the given direction. Given direction. But this is not always true. We have, so many processes, so many chemical reactions, so many physical phenomena that they are spontaneous in the given direction, but delta H is positive for them. Or even delta H is means energy change is 0. So we have various, physical and chemical processes and biological processes which are spontaneous in a given direction and which do not have this delta H is less than 0, or and proceed in the given direction without changing energy, right? So this statement is not always true, right? This not always true. Not always true, right? This is not always true. So we can see various examples which are spontaneous in a given direction with delta H positive. For example, first case, if you see solubility of NH4Cl in water, right? Delta H is positive for that, for this dissolution process, but it is spontaneous. Right? Similarly, if you see barium hydroxide, take ammonium nitrate, right? If you take barium hydroxide and ammonium nitrate, so this ammonium nitrate is this is aqueous and this is solid, right? This is solid. So you will get barium nitrate solid plus 2H2O liquid plus 2NH3 aqueous. See, this reaction is so fast and spontaneous despite delta H is positive here, and this is spontaneous, right? So and there are so many reactions we have that for them delta H is positive, so and they are spontaneous in the given direction. Similarly, some physical processes, like third example, if we can see that the expansion of an ideal gas against vacuum, right? So this process is spontaneous, but delta E is equal to 0 for this. There is no change in the temperature of the gas, although expansion is taking place, but there is no change in the internal energy, right? And the process is spontaneous in the given direction. Similarly, mixing of mixing of two gases at the same temperature, at the same temperature, right? Suppose that if you have two gases and at the same temperature, so delta E is equal to 0 for that, although their mixing is spontaneous. Spontaneous, right? So here we can say that entropy change or entropy is a driving force for chemical reactions and physical processes, particularly involving the microscopic state of matter, not for macroscopic state. So in the nature we have two driving forces. In the nature we have two driving forces. In the nature we have two driving forces. Driving forces. One is what? Energy. Other one is entropy. Energy as a driving force and entropy as a driving force. Mechanical processes, all mechanical processes can be explained with the help of energy, solely energy driven process. All the mechanical processes like movement of a car, movement of a bike, aeroplane, all these are purely mechanical processes and they can be explained on the basis of purely energy. No role of entropy here. Without use of entropy you can explain all these processes. Entropy driven processes are chemical reactions, and and physical processes. So but not all, we can say certain chemical reactions and certain physical processes that are solely entropy driven, not all, solely entropy driven. So we can differentiate here chemical reactions, some of the chemical reactions and physical processes are solely entropy driven. And second case of chemical reactions and physical processes, reactions and physical processes, they can be explained by both or derived derived by energy and entropy both. Entropy both. Right? So we have this first set, this is second set, and third set. We have certain chemical reactions and physical processes which are solely, they can be explained solely on the basis of energy. So we have three category of processes and chemical reaction. One, solely entropy driven. Second one, energy and entropy both are important and both can be used to explain those reactions and physical process. And third one is energy driven, right? I cannot say that there is no reaction which can be explained only with the help of energy. Yes, we have many reactions which are solely energy driven. So third category is chemical reactions and physical processes which are solely energy driven. Right? So you may get all these three types of reactions during your study of chemistry, whether you are studying organic chemistry or inorganic chemistry or any physical transformation. Either energy will derive or entropy will derive solely, or both will derive. So majority of reaction you have in this category that they are both energy and entropy driven, right? So we have three types of chemical reactions, chemical reactions and processes on the basis of the driving forces. One are solely entropy driven, number one. Second are energy and entropy both driven, and third solely energy driven processes. Right? Good. Now see, first we will I will discuss this different statements and what is second law. After that we will discuss we will define entropy and discuss about entropy. So see, first statement I am taking, that is Kelvin statement of Kelvin. So see, first we will try to understand what Kelvin has suggested through a diagram. Suppose that we have a reservoir, hot reservoir, having temperature T1. It is hot, right? Reservoir means if you take some heat from that object, temperature will not change, right? So means the reservoir, you can say a thermostat. A reservoir can be treated as a thermostat of which temperature is constant. So see, suppose that some heat is withdrawn from this hot reservoir, and one in a cyclic system we are doing work over the surrounding in a cyclic manner. So whatsoever heat we are taking from this hot reservoir Q, and we are doing the work on the surrounding, so this minus W, since this is a cyclic system, so delta E is equal to 0 for this, cyclic system, right? Cyclic system. So delta E is equal to 0. So you can write here, see here, Q is greater than 0, W is less than 0, because the work is done by the system on the surrounding, right? So you can write here Q is equal to minus W. So what Kelvin has suggested, this is the information extracted from thermodynamics first law. So what Kelvin said, that this type of system, this is impossible. This is impossible. Impossible, right? Means we, I mean, cannot devise, or we cannot make a system in which some heat is taken from a hot reservoir and totally convert this into the work, useful work, through a cyclic process. What Kelvin suggested? Kelvin suggested that if you take a hot reservoir at T1 temperature, T1 hot, right? And taking some heat, so in a cyclic manner we are doing work on the surrounding, minus W, and we are extracting Q1 heat from this hot reservoir. So there must be some heat transfer to another system, that is T2 temperature, and this is cold reservoir and this is hot reservoir. Means if you put some heat here, so I mean there is no change in the temperature. So in actual systems, what is the reservoir? Basically surrounding acts as a reservoir, right? Suppose that if you put some heat energy to the surrounding, there is no change of temperature because surrounding is so large. So this is the concept of here reservoir, right? So here some heat is given to the this cold reservoir, or you can say this is sink, right? Cold reservoir, this is hot reservoir. So this type of system, this is okay. This is okay. This is impossible and this is okay, right? Means if you take some heat from hot reservoir, do some work, part of that heat is transferred to the low temperature system, right? So in this case, Q1 is greater than 0, W is less than 0, and Q2 is less than 0. So you can write Q1 total heat, what is coming from this hot reservoir, that is minus W minus Q. So you can write this. So this is the means if you translate this in English, the whole representation, if you are able to translate this, that is the Kelvin's statement. So what is the translation of this? You can see it is impossible. It is impossible for any system, for any system to operate in a cycle, to operate in a cycle, this is important word, cycle, that takes heat from hot reservoir, heat from hot reservoir and convert it into into work in the surroundings, work on the surrounding, or in the surrounding, you can say. Surroundings without at the same time, without at the same time transferring some heat, transferring some heat to a cold reservoir, to a cold reservoir. So this is the statement of Kelvin, and you know this is the representation of a heat engine. Heat engine basically works on this concept, right? So this is the statement, first statement of second law given by Kelvin. Similarly, one more statement is that is given by Clausius, that is opposite of this, precisely opposite of this, that is Clausius statement, right? So that also I will explain, and after that we will take up this heat engine, and we will try to make the definition of entropy from here, right? Okay, now see Clausius statement. See what Clausius has suggested, that if we take a hot reservoir and cold reservoir, so if we take heat from cold reservoir and directly transfer to the hot reservoir, so this type of system, this is impossible. This is impossible. Means you cannot take heat from a cold reservoir and directly transfer the heat to the hot reservoir without converting some part of work into heat. Now see, this seems to be okay. This is okay. We are taking some heat from cold reservoir, and we are doing some work on the system so that W can be converted into the heat, and then it is possible that you can transfer the heat to the hot reservoir. So here Q2 is greater than 0, Q1 is less than 0, and W is greater than 0. So this time you can write minus Q1 is equal to Q2 plus W, W plus Q2. So this type of system is okay. So why we are taking always in a cyclic system? Obviously, we try to make the energy conserve. We try to put, design the system in which energy is conserved, right? So energy should be conserved. So we can define the next thermodynamic function, that is entropy, by using all these concepts. So this is Clausius statement. Now you can write the Clausius statement, same statement. So you know this is the concept of refrigerator. This is the concept of refrigerator, and this is the concept of heat engine. So Kelvin statement is the basis of the heat engine, and Clausius statement, it is the basis of the refrigerator, right? In the refrigerator, system is taking heat from relatively colder object and transfer to the hotter object. So here hot system is the environment, right? And here the cold reservoir in the heat engine, the cold reservoir, this is the surrounding, means I mean atmosphere, and this is the system, means here this is hot and this is cold. So this here, this is the heat engine. So in heat engine, this is the surrounding, or you can say atmosphere, and in refrigerator, this is atmosphere and this is our system, right? So we can write the statement, Clausius statement. So everybody has noted down this. Okay. So this is the I mean refrigerator, concept of refrigerator, and this type of system is impossible, right? So Clausius statement, same. It is impossible. It is impossible for any system, to operate in a cycle, to operate in a cycle that takes heat, that takes heat from a cold reservoir, from a cold reservoir and transfers it to a hot reservoir, hot reservoir without at the same time converting some work converting some work some work into heat, so this is the Clausius statement, right? So this is I mean very much clear from here, right? And energy is conserved in both the cases, whether it is heat engine or this is refrigerator. Alternatively, also Clausius has suggested some point that this is the alternative statement of Clausius, that all spontaneous process, right, are are irreversible. Irreversible. That is, I mean, we can say heat flows from hot to cold, cold spontaneously and irreversibly, right? This is important. So this is alternative statement given by Clausius, and this is always true, right? Here, see, it is not possible. This process is not a spontaneous process, right? This is not a spontaneous process because this is against the gradient rule, or as we have seen, the temperature is a potential, so that this violates that point, right? this is okay. This is okay that heat can flow from hotter body to colder body spontaneously. So this is alternative statement suggested by Clausius, right? Now mathematical statement, what we can write here, that second law mathematical statement, and we will try to justify this statement in the coming points, that cyclic process delta q reversible by t, right, this is equal to 0, and cyclic delta q irreversible by t is less than 0. This is the mathematical basis of second law. So mathematical statement, mathematical statement, right? So as we know that this delta q by t, this is a state function, is a state function, and known as what? Entropy. This is known as what? Entropy. So we will justify this, how this is equal to 0, and this is what, less than 0 in a cyclic process. So we will try to justify this, these mathematical statements, and try to link this statement with the Kelvin statement or Clausius statement. So Clausius and Kelvin statement and this mathematical relation can be linked together, and then we can define this entropy, right? Now see, the Carnot cycle, a typical heat engine. Typical heat engine means this engine exists on the paper. You cannot prepare such type of engine in real sense. So here all paths are reversible. This is a cyclic, process. So from 1 to 2, this is the isothermal expansion. Then adiabatic 2 to 3, this is adiabatic expansion. 3 to 4, this is isothermal at different temperature. This is at T1, this is at T2, and that this is adiabatic compression. So this cycle basically composed of 4 steps: isothermal expansion, adiabatic expansion, isothermal compression, and then finally adiabatic compression. So one thing is clear here, that delta E is equal to 0 for the this entire cycle. This is true, always true. So I am taking this one by one step and writing all the variables which is required. So 1 to 2, if you see 1 to 2, so delta E is equal to 0, this individual step, delta E is equal to 0. So we can write here Q1, first step, Q1 is equal to minus of W1. Q1 is equal to minus of W1, and this is equal to minus uh, minus P external dV, and this is a reversible process, so you can write here this is what, 1 to 2 nRT dV by V, so you can write this nRT1. So this is n is equal to 1 mole, we can take here 1 mole. So N is equal to 1 mole. So this is equal to RT1 ln V2 by V1. This is V2 and this is V1, right? So this is your the heat and work change, heat and work involved in from 1 to 2. Now come to the step 2. From 2 to 3. From 2 to 3, delta Q is equal to 0 since it is adiabatic process. So we can write here W1 dash I am taking here work. So W1 dash is equal to CV T2 minus T1. This is very simple. You can write. This is equation 2. And one more point you can write here, because temperature is not constant. Here temperature is T1, here temperature is T2. So you can write T2 by T1 is equal to what? V3 and V2. So V2 by V3. V2 by V3. This we have already done this in adiabatic expansion, gamma minus 1, right? Gamma minus 1. This is equation 3. So this is step 2. Now come to the third step, 3 to 4. So 3 to 4, again delta E is equal to 0. Delta E is equal to 0. So this time you can write heat change Q2 is equal to minus W2. This time I am taking W2 work. So Q2 is equal to minus of W2. So this is equal to, we can write RT2 ln V4 by V3. V4 by V3. Right? We can write this. This is equation 4. Right? And now 4 to 1 adiabatic compression. 4 to 1, this is adiabatic compression. So this time delta Q is equal to 0. So you can write W2 dash is equal to CV T1 minus T2. Because at this point temperature is T1 and this point temperature is T2. So T1 minus T2, right? And this is equation 5. And one more equation we can write here, that T1 by T2, T1 by T2, this is final by initial, T1 by T2 is equal to V4 by V2, V4 by V1, not V2, V4 by V1, because we are moving 4 to 1, gamma minus 1. This is equation 6. So this we can write in a very simple manner for all the steps. Already I have I mean derived all these formulas. There is no need to further derive all these formulas, right? So now we can write here from equation 5 and 3 and 6. See what we can write? Equation 3 and 6. If you take equation 3 and 6, so what we can write here? T1 by T2, T2 by T1 and T1 by T2. So we can write here V1 by T2 by T1. So this also we can write. So this we can write
don't make this equation 6. First we change this equation, or we can write here T2 by T1 is equal to V1 by V4 to the power gamma minus 1. This is equation 6. So now you can write from equation 3 and 6 that V2 by V3 to the power gamma minus 1 is equal to V1 by V4 to the power gamma minus 1. So you can write here V2 by V3 is equal to V1 by V4. So you can write, or V1 by or you can write V2 by V1. V2 by V1 is equal to V3 by V4. So this is equation 7, right? Now see, if we want to calculate Q2 by Q1, so Q2 by Q1 is equal to, you can write T2 ln RT2 ln what is the value? V4 by V3 divided by RT1 ln V2 by V1, the first equation, V2 by V1, right? V2 by V1. So this you can write, R and R cancel, T2 by T1 ln V4 by V3 is equal to V1 by, so V4 by V3 is equal to or V3 by, so we can write here minus ln V3 by V4 divided by ln V2 by V1. So this you can write minus T2 ln V3 by V4 from equation 7, you can write V2 by V1, V2 by V1 by T1 ln V2 by V1, right? So you can write here Q2 by Q1 is equal to minus of T2 by T1. So this is the result of what? This Carnot engine, a cyclic process. So you can write here, or you can write Q1 by T1 is equal to minus of Q2 by T2, right? You can write, or you can write Q1 by T1 plus Q2 by T2 is equal to 0, right? Or you can write delta Q reversible by T is equal to 0. So this is what mathematically I have written for this entropy. See, this is called what? Entropy. Q by T is called entropy. What mathematically here I have written, I mean Clausius suggested basically this, that this is equal to 0 and Q reversible is less than 0, and delta Q by T is a state function. So here C Q by T is a state function because the cyclic integration, it is equal to 0. So this is the justification of this Clausius and Kelvin's statement with the mathematical definition of entropy, right? So in this way you can justify that this Q by T in the complete cycle, the ratio of Q by T, it is always equal to 0 if all the steps are reversible. If all the steps are reversible, right? Okay, now see, if you want to calculate the efficiency of this heat engine or efficiency of this cycle, so you can use very simple formula. Efficiency, this is represented by this epsilon, or you can say simply you can write E. So this is equal to the work output to the surrounding, work output to the surrounding divided by heat taken from the hotter body. Hot reservoir, right? So total work performed in this complete cycle, and definitely this is I mean T1 is more than this T2, right? So hotter body T1. So this is equal to, you can write here surrounding, so negative sign will come with the W1 plus W1 dash plus W2 plus W2 dash whole divided by what? Q1. So this is what efficiency of this cycle, right? So this is equation 8. Now you can see, if you add all this from the first law, you can write here from the first law that this delta E is equal to 0. So you can write here Q1 plus Q2 is equal to minus of W1 plus W1 dash plus W2 plus W2 dash, right? Or minus of W cycle in the complete cycle. This is equation 9. So you can write efficiency is equal to efficiency of heat engine is equal to minus of this minus of W is equal to, you can write Q1 plus Q2 by Q1, right? So this is equal to 1 plus Q2 by Q1. And Q2 by Q1, we have already proved that Q2 by Q1 is equal to minus T2 by T1. So one more formula we have, minus T2 by T1. So this is the formula for efficiency. And T1, what is T1 here? T1 is the temperature of hot reservoir. T2 is the temperature of cold reservoir, right? Q1 is the heat taken from the hot reservoir, taken from hot reservoir, and Q2 is the heat transferred to the cold reservoir, right? So in this way you can calculate, or you can numerically find out what is the efficiency of what engine. So heat engine, right? And you see here Q2 is what? Q2 is transferred to the cold, so Q2 is less than 0, as we know that Q2 is less than 0. So the efficiency, that is efficiency is what? It is represented by E. This is less than 1. I mean less than 100%. So for any, I mean such Carnot engine or heat engine, efficiency is always less than what? 100%. And what is this minus W? Minus W is equal to Q1 into efficiency E, and this is called what? Work output. So work output, if it is asked, what is the work output? So work output, if efficiency is given and heat taken from the hot reservoirs is given, so you can calculate the work output by using this formula, right? So this is all about this, I mean efficiency of any heat engine. One more interpretation we can do here, that efficiency E is equal to efficiency is equal to 100%. Theoretically, it is possible, right? As T2 is close to, or T2 is equal to 0 Kelvin. So if T2 is equal to 0 Kelvin, so in this situation efficiency is 100%. But from the thermodynamics third law, it is impossible, or it is what you cannot approach this T2 is 0 Kelvin. So that put the restriction here, thermodynamics third law. But theoretically, you can say, okay, efficiency may be equal to 100%, but if you take T2 is equal to 0 Kelvin, but this is not possible, right? So this is all about Carnot engine, Carnot cycle, heat engine, and efficiency of any heat engine, and the ratio of Q by T is constant in a cyclic process, which is I mean made in this isothermal and adiabatic cycle, theoretical cycle, that is known as Carnot cycle. So this ratio of Q by T is known as I mean entropy, and this is the mathematical definition of entropy. I will define the physical definition as well for entropy, right? But before going into the detail of that physical definition of entropy and dependency of entropy, that entropy depends on what factors. One more thing I have to explain here, that I have explained this Q reversible is equal to 0 in a reversible cycle, but what about this Q irreversible? How to justify this delta Q reversible by T irreversible by T is less than 0? So in the I mean next lecture I will take up this. First I will prove this. After that I will define physically I mean entropy, right?